You are trapped right now as you read these words. You exist inside an invisible prison. A sphere exactly 46 billion light years in radius surrounds you, surrounds Earth, surrounds everything you have ever known or will ever know. This is not science fiction. This is not a metaphor. This is the cold, hard reality of our existence in this universe. No matter what technology humanity develops, no matter how advanced our civilization becomes, no matter how desperately we try, we can never, ever escape this cosmic cage. We are prisoners of the universe itself, confined by the very structure of space and time to a tiny bubble of reality. Everything beyond this sphere, everything outside our prison, is forever unreachable. Not unreachable with current technology, not unreachable until we invent faster ships. Forever unreachable, fundamentally, physically, absolutely impossible to ever access. The walls of our prison are not made of matter or energy. They are made of something far more impenetrable. They are made of the fabric of space-time itself. And these walls are closing in. Let me be clear about what we are actually discussing here. When astronomers talk about the universe, they are almost always referring to the observable universe. This is a critical distinction that most people do not understand. The observable universe is not the entire universe, it is merely the portion of the universe from which light has had enough time to reach us since the Big Bang. Think about what this means. The universe began approximately 13.8 billion years ago in an event we call the Big Bang. Light travels at a finite speed, roughly 186,000 miles per second. This means that light from distant objects takes time to reach us. We see the sun as it was 8 minutes ago because that is how long light takes to travel from the sun to Earth. We see the nearest star system, Alpha Centauri, as it was about 4 years ago. We see the Andromeda galaxy as it was 2.5 million years ago. The farther we look into space, the farther back in time we are seeing. The most distant objects we can observe are so far away that their light has been traveling toward us for most of the age of the universe itself. These objects sit at the edge of our observable bubble, at the cosmic horizon. This horizon represents the farthest distance from which light has had time to reach us since the beginning of everything. Beyond this horizon, objects are so far away that their light simply has not had enough time to complete the journey to Earth. Not yet anyway. Those objects exist. They are out there right now, but we cannot see them. We cannot detect them. We cannot prove they exist, even though logic and mathematics tell us they must be there. This boundary, this cosmic horizon, is as real as any wall you have ever touched. It is a physical limitation imposed by the universe itself. The horizon exists because of two fundamental facts that cannot be changed. First, light travels at a finite speed. It does not move instantaneously. It takes time for light to cross space. Second, the universe has a finite age. It has not existed forever. It began 13.8 billion years ago. Combine these two facts and you get an inescapable conclusion. There is a maximum distance from which light could possibly have reached us. This maximum distance defines the edge of the observable universe. It creates our cosmic prison. The horizon is not a failure of our telescopes. It is not a temporary limitation that better technology will overcome. It is built into the fundamental structure of reality. Even a telescope with perfect infinite resolution and sensitivity would still be unable to see beyond this horizon. The light from objects beyond the horizon has not arrived yet. It is still traveling through space, still on its way, but it is not here. We are waiting for light that left its source billions of years ago, light that has been crossing the cosmos since before Earth existed, since before our sun was born, since before our galaxy took its current shape. And for objects beyond the horizon, we will wait forever. Imagine standing in the middle of a vast dense fog. You can see clearly for about 100 yards in every direction. Beyond that distance, the fog becomes too thick. The world continues beyond your circle of visibility. You know this. You can reason that there are trees, hills, rivers, cities beyond the fog, but you cannot see them. You cannot confirm they exist. You cannot observe them directly. Now imagine that you cannot move. You are fixed in place, unable to walk forward to expand your visible area. The fog is permanent, it will never lift. You will stand in that spot for your entire existence, able to observe only what lies within your 100-yard circle of visibility. Everything beyond is theory, assumption, educated guesses, based on what you can see within your limited range. This is humanity's situation on a cosmic scale. We sit inside our observable bubble, able to see approximately 46 billion light years in every direction. Beyond that distance lies the cosmic fog, the horizon we cannot penetrate. We know the universe continues beyond our bubble. We can reason that more galaxies exist out there, more stars, more planets, perhaps more life. But we cannot see them. We cannot reach them. We cannot confirm anything about them. We are stuck in our circle of cosmic visibility, unable to expand it in any meaningful way. Here is where things get strange. If the universe is only 13.8 billion years old, why is the observable universe 46 billion light years in radius? Should it not be 13.8 billion light years? The light has been traveling for 13.8 billion years, so surely it has covered a distance of 13.8 billion light years. Right? Wrong. This confusion arises because space itself has been expanding during the time light has been traveling. When a distant galaxy emitted the light we see today, that galaxy was much closer to us than it is now. The light began its journey toward Earth when the universe was smaller. As the light traveled through space, space itself was stretching. The galaxy that emitted the light was being carried away from us by cosmic expansion. By the time the light finally reaches our telescopes, that galaxy is no longer at the location where it emitted the light. It has moved much, much farther away. Current observations and calculations suggest that the most distant observable objects, the ones at our cosmic horizon, are now about 46 billion light years away from us. Their light has been traveling for 13.8 billion years, but cosmic expansion during that journey means the sources of that light are now at a distance of 46 billion light years. This creates our prison radius. Everything within this 46 billion light year sphere is in principle observable. Everything beyond it is not. The boundary is absolute. What exists beyond our observable bubble? What lies outside the prison walls? Cosmologists have developed theories based on observations of what we can see. The universe appears remarkably uniform on the largest scales. In every direction we look, we see roughly the same thing: galaxies, galaxy clusters, vast cosmic webs of matter, enormous voids of empty space. The statistical properties of the universe appear identical whether we look north, south, east, west, up, or down. This uniformity suggests a principle that cosmologists call homogeneity and isotropy. The universe looks the same everywhere and in all directions. If this principle holds true beyond our observable bubble, and most scientists believe it does, then what lies beyond our horizon is probably more of what we see within it. More galaxies arranged in similar patterns, more stars, more planets, more of everything. The universe beyond our prison walls likely resembles the universe within them. It is not a different realm with alien physics or exotic structures. It is simply more space, more matter, more cosmos extending outward. If the universe is infinite, which many cosmological models suggest, then our observable bubble is an infinitesimally small sample of everything that exists. Imagine an infinite ocean. You are floating in that ocean, able to observe the water within arm's reach. What you see within arm's reach is the observable universe. The infinite ocean beyond your reach is the rest of reality, forever hidden from your view. Here is the statistic that should terrify and humble you in equal measure. If the universe is infinite, our observable region contains 0% of everything that exists. Literally zero, not a small percentage, not a tiny fraction. Zero. Infinity divided by any finite number equals infinity. Our 46 billion light year radius bubble, as vast as it seems, as full of galaxies and wonders as it is, represents exactly none of the total universe. Every galaxy we have ever observed, every star that has ever been cataloged, every planet we have discovered, every black hole we have studied, every cosmic phenomenon we have measured, all of it together represents 0% of reality. Even if the universe is not infinite, even if it is merely unimaginably large rather than literally endless, we are still trapped observing less than 4% of what exists. Some cosmological models suggest the total universe is at least 250 times larger than the observable universe. Even in these finite models, we can observe less than 4% of reality. More than 96% of everything that exists is beyond our cosmic horizon, locked away forever, fundamentally inaccessible to observation, measurement, or interaction. Entire superclusters of galaxies exist beyond our view. Hundreds of billions, perhaps trillions of galaxies that we will never see. Countless stars that will never appear in any telescope. Uncountable planets, some of which might harbor life, civilizations, perhaps even intelligence that evolved and thrived and fell without us ever knowing they existed, all of it beyond the wall. Here is the paradox that makes our cosmic prison even more disturbing. The observable universe is growing. Every second that passes, light from slightly more distant objects has time to reach us. Our bubble of observability expands by approximately 1 light second every second. That is about 186,000 miles of new space coming into view each second. Every day, we can theoretically observe about 16 billion miles farther into the cosmos. This sounds like good news. Our prison is getting bigger, our walls are expanding outward, we are gaining access to more of the universe. But this expansion of observability is an illusion of progress. Yes, we are seeing farther. Yes, more light from more distant objects is reaching us. But at the same time, cosmic expansion is carrying distant galaxies away from us at ever increasing speeds. Galaxies that are currently within our observable universe will not remain observable forever. Due to accelerating cosmic expansion, driven by the mysterious force we call dark energy, space between us and distant galaxies is stretching faster and faster. Galaxies at the edge of our observable universe are receding from us at tremendous velocities. Some are receding faster than the speed of light, not moving through space faster than light, which would violate physics, but being carried by expanding space itself. As these galaxies accelerate away from us, their light becomes increasingly redshifted, stretched to longer and longer wavelengths by the expansion of space. Eventually, the light becomes so redshifted that it effectively disappears, fading beyond any possible detection. The galaxies do not literally vanish, they simply fade from view, as their light is stretched beyond the infrared, beyond radio waves, into wavelengths so long they become meaningless. This process is accelerating. Every day, galaxies are crossing the cosmic event horizon, a boundary beyond which they are receding faster than light from us could ever travel to reach them. Once a galaxy crosses this boundary, we can still see it for a time. The light it emitted before crossing the horizon continues to arrive, but we are seeing an increasingly outdated image of that galaxy. We see it as it was in the distant past, frozen in time, never able to observe what happens to it after it crosses the horizon. Eventually, even this light will be stretched beyond detection, and the galaxy will effectively cease to exist from our perspective. It will be gone, not destroyed, but removed from our observable universe, expelled from our cosmic prison into the unreachable beyond. Calculations suggest that in the distant future, in about 100 billion years or so, only the galaxies in our local group will remain observable. The Milky Way, Andromeda, and a few dozen smaller satellite galaxies will have merged into one massive galaxy. Beyond this merged local group, the universe will appear empty, dark, void. Every distant galaxy will have been carried beyond the horizon by cosmic expansion. Future astronomers living in that era will look out at the cosmos and see nothing. No distant galaxies, no cosmic web structure, no evidence of the rich universe we observe today. They will conclude they live in a small, isolated island of matter surrounded by infinite empty space. They will have no evidence that billions of other galaxies ever existed. The cosmic microwave background radiation, the echo of the Big Bang that we can detect today, will have been redshifted into undetectability. Future scientists will lack the very evidence that allowed us to understand cosmic origins and evolution. They will be more trapped than we are, prisoners in an even smaller cell, with even less of the universe accessible to them. The walls of our prison are not static, they are dynamic, shifting, changing. In some sense, they are closing in. We like to think of scientific progress as a steady march toward greater knowledge, greater understanding, greater access to the cosmos. We imagine future civilizations with incredible technology exploring vast reaches of space, visiting distant galaxies, making contact with alien civilizations across the universe. This is a comforting fantasy. The reality is darker. We live in a golden age of cosmic observability. We exist at a time when the universe is old enough to have formed rich structure, galaxies and stars and planets in abundance, but young enough that cosmic expansion has not yet carried most of this structure beyond our horizon. Past astronomers, had they existed billions of years ago, would have seen a younger, simpler universe with less structure. Future astronomers, billions of years hence, will see an older, emptier universe with less observability. We occupy a special moment, a temporary window when the cosmos is both mature and visible. This window is closing. Every moment that passes, we lose access to more distant galaxies. Every year, more of the universe slips beyond the horizon. Humanity has existed for mere moments on cosmic timescales. We developed astronomy and cosmology only in the last few centuries. We have had powerful telescopes capable of observing the deep universe for only decades. We are racing to observe and understand as much as we can before it is too late, before the expanding universe carries the evidence beyond our reach forever. But the prison walls, the cosmic horizon, represents more than just a limit on what we can see. It represents a fundamental boundary in the structure of space-time itself. This is not merely about light that has not arrived yet. This is not simply about distances too vast to travel. The cosmic horizon marks a real physical division in the causal structure of the universe. Events beyond the horizon cannot affect us. Information from beyond cannot reach us. The laws of physics themselves create this impenetrable barrier. In the coming parts of this exploration, we will dig deeper into why this wall exists, what creates it, and why no technology, no matter how advanced, can ever breach it. We will examine the role of light speed, the nature of cosmic expansion, and the terrifying acceleration that is making our prison smaller and more isolated with each passing moment. We will confront the uncomfortable truth that we are not just limited by technology or knowledge. We are limited by reality itself. The universe has built walls around us that cannot be broken, cannot be climbed, cannot be tunneled under. We are here in this bubble, observing this fraction of reality, and we will never, ever leave. The question is not whether we can escape. The question is what we do with the knowledge that we are trapped. The universe has a speed limit. This is not a suggestion. This is not a guideline that advanced civilizations might find ways around. This is an absolute fundamental law of reality itself. Nothing can move faster than light, nothing. The speed of light in a vacuum is exactly 182 miles per second, or if you prefer metric, about 299,792 kilometers per second. This number is not arbitrary. It is not the result of light trying really hard to go fast. It is woven into the mathematical structure of space-time itself. Light speed is the speed at which causality propagates through the universe. It is the speed at which information can travel from one point to another. It is the cosmic speed limit, and this speed limit is precisely what creates the walls of our prison. Understanding why nothing can exceed this speed, and what happens when cosmic expansion makes even light speed insufficient, is essential to understanding why we are trapped forever. In 1905, Albert Einstein published his theory of special relativity and changed our understanding of space, time, and motion forever. Before Einstein, scientists assumed that if you kept accelerating an object,
adding more and more energy. It would go faster and faster without limit. If you had enough fuel, enough power, enough time, you could
accelerate a spacecraft to any speed you wanted. Einstein proved this intuition catastrophically wrong. He showed that space and time are not separate things, but are united into a single four-dimensional fabric called spacetime. He demonstrated that the laws of physics must work the same way for all observers, regardless of their motion. From these principles, he derived something shocking. As an object with mass accelerates closer and closer to the speed of light, something strange happens. The object becomes more massive. Not more massive in the sense of gaining more particles or atoms, but more massive in terms of inertia, in terms of how much energy is required to accelerate it further. The faster you go, the harder it becomes to go even faster. As your speed approaches light speed, your mass approaches infinity. Accelerating an infinite mass requires infinite energy. The universe does not contain infinite energy. Therefore, nothing with mass can reach light speed, let alone exceed it. You can accelerate closer and closer, reaching 99% of light speed, then 99.9%, then 99.99%, but you will never touch 100%. The closer you get, the more energy each additional increment requires. You asymptotically approach light speed but never reach it. This is not an engineering problem. This is reality telling you that light speed is the absolute ceiling, the ultimate barrier, the cosmic law that cannot be broken. Light itself, photons, particles with no mass, travel at exactly this speed limit. They do not accelerate to light speed, they are created already, moving at light speed and never slow down. Photons experience no time. From a photon's perspective, if such a thing could be said to exist, it is emitted and absorbed in the same instant, regardless of how many billions of years pass from our perspective during its journey. But here is the critical point that most people miss. Even light traveling at the ultimate cosmic speed limit cannot outrun the expansion of space itself. This is where our prison becomes truly inescapable. Light speed is fast by any human standard. A photon could circle the Earth's equator 7.5 times in 1 second. It could reach the moon in about 1.25 seconds. It could cross the solar system in hours. It could reach the nearest star in just over 4 years. On human scales, light speed seems instantaneous, but the universe is not built on human scales. The universe is vast beyond human comprehension, and it is getting bigger. Space itself is expanding, stretching, growing. This expansion does not move galaxies through space, it enlarges the space between galaxies. And there is no law of physics that prevents space itself from expanding faster than light can cross it. In fact, in most of the universe, this is exactly what happens. Space expands so quickly that light trying to cross it makes no progress. The light keeps moving forward at 186,282 miles per second, but the space ahead of it is stretching faster than the light can cover the distance. The photon is running on a cosmic treadmill that accelerates faster than the photon can run. It will run forever and never reach its destination. This creates what scientists call a cosmic traffic jam. Imagine a highway where cars are trying to drive forward, but the road itself is stretching. The cars are moving at highway speeds, but between each car and the next, more road is being created faster than the cars can drive. The distance between cars keeps increasing, even though all cars are driving forward as fast as they can. Now imagine that this road stretching accelerates over time. The road stretches faster and faster. Eventually, cars that are far apart will be separated by regions of road that are stretching faster than the cars can possibly drive. These cars become permanently separated. A car in the front can flash its headlights, but those light beams will never reach the cars far behind because the road between them is stretching too quickly. The cars behind are receding into the distance, not because they are driving backward, but because the road itself is expanding. This is our universe. Galaxies are the cars, light from those galaxies are the headlights, the expanding road is space itself, and we are in one of those cars watching other cars recede into the distance, knowing that we will never be able to catch up to them, never be able to communicate with them,
never be able to reach them. They are disappearing beyond our cosmic horizon, and there is nothing we can do about it. The mathematics of this cosmic recession was first discovered by Edwin Hubble in the 1920s, though he did not fully understand what he was seeing. Hubble observed distant galaxies and measured their velocities by examining how their light was redshifted. Redshift occurs when an object emitting light is moving away from you. The light waves get stretched to longer, redder wavelengths. By measuring how much redshift each galaxy exhibited, Hubble could calculate how fast that galaxy was receding. What he found was stunning. The farther away a galaxy was, the faster it was receding. This relationship, now called Hubble's law, shows a direct proportionality. Double the distance, double the recession velocity. Triple the distance, triple the recession velocity. The current measurements give us what is called the Hubble constant, though calling it a constant is slightly misleading, since its value changes over cosmic time. Right now, the Hubble constant is approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So for every 3.26 million light years of distance, the recession velocity increases by about 70 kilometers per second. A galaxy 3.26 million light years away recedes at 70 kilometers per second. A galaxy 6.52 million light years away recedes at 140 kilometers per second. A galaxy 32.6 million light years away recedes at 700 kilometers per day.
Second, you can see where this is going. Keep extending the distance, and eventually you reach galaxies that are receding at velocities approaching the speed of light, and beyond that, galaxies receding faster than light. Let us do the math. The speed of light is about 300,000 kilometers per second. Using the Hubble constant of 70 kilometers per second per megaparsec, we can calculate the distance at which recession velocity equals light speed. Divide 300,000 by 70 and you get about 4,300 megaparsecs. Multiply that by 3.26 million light years per megaparsec and you get approximately 14 billion light years. This is the distance at which galaxies are receding from us at exactly the speed of light. This boundary is called the Hubble sphere. Galaxies closer than 14 billion light years are receding slower than light. Galaxies farther than 14 billion light years are receding faster than light. This is not science fiction, this is observed reality. We have detected galaxies beyond this threshold. We can see them because the light they emitted long ago when they were closer to us has finally reached us after billions of years of travel. But those galaxies are now receding faster than light. Any light they emit right now will never reach us. It will travel toward us at 300,000 kilometers per second, but the space between us and them is expanding at a rate greater than 300,000 kilometers per second. The light makes no net progress toward us. It is trapped, frozen in space, running forward, but getting nowhere. This creates a cosmic event horizon, similar in concept to a black hole's event horizon, but inverted. Around a black hole, anything that crosses the event horizon cannot escape because space is falling into the black hole faster than light can climb out. In our expanding universe, anything beyond the cosmic event horizon cannot reach us because space is expanding faster than light can cross it. What does this mean for galaxies beyond the threshold? They become causally disconnected from us. Causality is the relationship between cause and effect, between events that can influence each other. Two regions of space are causally connected if a signal traveling at light speed can travel between them. If light cannot make the journey, then the regions are causally disconnected. Nothing that happens in one region can ever affect the other. No information can transfer between them. No communication is possible. No interaction can occur. For all practical purposes, for all physical purposes, for all purposes that matter, they might as well exist in separate universes. A galaxy beyond our cosmic event horizon is lost to us forever. We cannot send signals to them. We cannot travel there. We cannot learn anything new about them. We can only observe the ancient light they emitted billions of years ago when they were closer and still within reach. We are watching ghosts, images of galaxies as they were in the distant past, frozen in time, never able to see what they have become. Those galaxies exist right now at this very moment, continuing their evolution, forming new stars, perhaps harboring life or even civilizations. But we will never know. They are beyond the wall, outside the prison, in the unreachable beyond, and every day more galaxies cross this threshold. Every day the wall closes in a bit more. But wait, you might say, what about Andromeda? The Andromeda galaxy is about 2.5 million light years away, well within the Hubble sphere, yet astronomers tell us that Andromeda is not receding from us. In fact, Andromeda is moving toward us. It is approaching at about 110 kilometers per second, and in approximately 4 billion years, it will collide with the Milky Way. How can this be? If the universe is expanding and all galaxies are receding according to Hubble's law, why is Andromeda approaching? The answer reveals an important nuance about cosmic expansion. Hubble's law describes the overall expansion of space on the largest cosmic scales. It is a statistical relationship that applies when you average over vast distances. But on smaller scales, local gravity can and does overcome cosmic expansion. The Milky Way and Andromeda are both massive galaxies. They exert strong gravitational attraction on each other. This gravitational pull is stronger than the expansion of space in the region between them. Gravity wins. The two galaxies are falling toward each other just as objects fall toward Earth despite any expansion of space. Our entire local group of galaxies, which includes the Milky Way, Andromeda, Triangulum, and dozens of smaller dwarf galaxies, is gravitationally bound. Expansion does not tear it apart because gravity holds it together. The same is true for galaxy clusters. Galaxies within a cluster orbit each other and remain bound despite cosmic expansion. But on larger scales, beyond galaxy clusters, gravity becomes too weak to overcome expansion. Superclusters, enormous collections of galaxy clusters spanning hundreds of millions of light years, are not gravitationally bound. They are being torn apart by expansion. Different parts of a supercluster are receding from each other. On the very largest scales, expansion dominates completely, and Hubble's law applies. So Andromeda is an exception, a nearby neighbor close enough that we share a gravitational relationship stronger than the expansion trying to separate us. But make no mistake, the vast majority of galaxies in the universe are receding from us, and the more distant they are, the faster they recede. When we observe these distant receding galaxies, we see them as they were in the ancient past. A galaxy 10 billion light years away is seen as it was 10 billion years ago, when the universe was only about 3.8 billion years old. We cannot see what that galaxy looks like today. We cannot observe its current state. The light showing us the galaxy's current state will not reach us for another 10 billion years. By the time that light arrives, assuming it ever does, the galaxy will have aged another 10 billion years and moved even farther away due to continued expansion. We are always looking at the past, never the present. For nearby objects, this delay is negligible. We see the sun as it was 8 minutes ago, close enough to the present that it makes little practical difference. But for distant galaxies, we are seeing ancient history. We are observing galaxies that may not even exist anymore in their current form. They may have collided with other galaxies, been torn apart by tidal forces, collapsed into black holes, or evolved beyond recognition. We have no way of knowing. We see them frozen at a moment billions of years in the past, and that ancient image is all we will ever have. This creates a strange situation where we are surrounded by ghosts. Every distant galaxy is a phantom, an echo, a memory of something that was but may no longer be. We are living in a universe where the present is inaccessible and only the past is visible. The farther we look, the deeper into history we peer until we reach the cosmic microwave background radiation, light from 380,000 years after the Big Bang, the oldest light that can possibly reach us, the ultimate horizon beyond which we cannot see. There is another layer of confusion that trips up even educated people trying to understand cosmic distances. When we say a galaxy is 10 billion light years away, what exactly do we mean? The light from that galaxy has been traveling for 10 billion years.
that is the light travel time. But during those 10 billion years, space has been expanding, the galaxy has been moving farther away. So, where is that galaxy right now at this very instant as we observe its ancient light? The answer is that the galaxy is now much farther away than 10 billion light years. Depending on the expansion rate and when exactly the light was emitted, that galaxy might now be 15 or 20 billion light years away, or even farther. Cosmologists distinguish between different kinds of distance. There is light travel time distance, which is how long the light has been traveling. There is comoving distance, which accounts for expansion and represents where the object is now in the expanding coordinate system. There is luminosity distance, which relates to how bright the object appears. There is angular diameter distance, which relates to how large the object appears in the sky. All of these distances give different numbers for the same object because space is expanding. This is not a failure of definition. It is a necessary consequence of measuring distances in an expanding universe. The, the key point is that the most distant observable galaxies are now about 46 billion light years away in co-moving distance, even though the light we see has only been traveling for about 13.8 billion years. The galaxies were much closer when they emitted that light, but expansion has carried them to their current, much greater distance. All of this brings us to the core reality that creates our cosmic prison. Light speed is the ultimate speed limit, nothing can go faster. But even traveling at this ultimate speed is not fast enough to escape the expansion of space itself. Space does not care about speed limits. Space is not moving through anything. Space is the stage upon which motion occurs, and the stage itself is growing. When space expands faster than light can cross it, light becomes trapped. Photons keep moving forward at their constant speed, but they make no progress toward their destination because new space is being created between them and their target faster than they can close the gap. This is happening right now throughout most of the universe. The majority of the cosmos consists of regions where space is expanding faster than light can traverse it. These regions are forever beyond our reach. We are trapped in a local bubble, a region where light can still make progress, where signals can still propagate, where causality still connects us to what we observe. Beyond this bubble lies the vast expanse of the universe, where space has pulled everything beyond the point of no return. The prison walls are not made of matter or energy. They are made of geometry, of space-time itself. And geometry is far harder to escape than any physical barrier. You cannot tunnel through geometry. You cannot fly over it. You cannot break it down or blast through it. The walls are absolute because they are written into the mathematical structure of existence itself. But we have only scratched the surface of why escape is impossible. Light speed creates the foundation of our prison, but cosmic expansion builds the walls higher and higher. Space is not just expanding, the expansion is accelerating. The universe is growing faster now than it was a billion years ago, and it will grow even faster a billion years from now. This acceleration, driven by the mysterious dark energy that permeates all of space, is making our prison smaller and more isolated with each passing moment. In the next part, we will explore exactly how this expansion works, why it is accelerating, and what this means for the future of observability. We will confront the disturbing reality that we are not just limited by light speed. We are limited by the active, ongoing, accelerating expansion of the very fabric of reality. The walls are closing in. The universe is pulling itself apart. And we are powerless to stop it. Space itself is stretching. This is not a metaphor, this is not poetic language, this is literal, physical reality. The fabric of space, the three-dimensional stage upon which all matter and energy exist, is actively growing, expanding, stretching like elastic, being pulled in all directions at once. When we say the universe is expanding, most people imagine galaxies flying away from each other like shrapnel from an explosion, moving through empty space to increasingly distant positions. This mental picture is completely wrong.
Galaxies are not moving through space, space itself is expanding, and galaxies are being carried along for the ride. They are embedded in the fabric of space like raisins in bread dough. When you bake bread, the dough rises. As it rises, the raisins inside do not move through the dough, they remain stationary relative to the dough immediately surrounding them. But the raisins get farther apart from each other because the dough between them is expanding. Each raisin sees every other raisin moving away. The farther apart two raisins are, the more dough exists between them, and therefore the faster they separate as that dough expands. This is cosmic expansion. Galaxies are the raisins, space is the dough is rising, and there is nothing anyone can do to stop it. The classic analogy that cosmologists use involves a balloon. Imagine the surface of a balloon with dots drawn on it. These dots represent galaxies. Now begin inflating the balloon. As the rubber surface stretches, the dots move farther apart from each other. A dot on one side of the balloon sees all other dots receding. The farther away another dot is, the faster it appears to recede because more rubber surface exists between them and all of that surface is stretching. Notice something critical about this analogy. There is no special dot at the center. Every dot sees the same thing. Every dot perceives itself as stationary while all other dots move away. There is no privileged position, no cosmic center from which expansion emanates. The expansion is happening everywhere uniformly at every point in space. If you are on one galaxy looking out, you see all other galaxies receding. If you magically transported yourself to a galaxy a billion light years away, you would still see all galaxies receding from your new position. Expansion looks the same from everywhere. This is a fundamental property of cosmic expansion. There is no center because every point is the center from its own perspective. The balloon analogy has a limitation we should address. The balloon surface is two-dimensional and it expands into the three-dimensional space surrounding it. This leads people to ask what the universe is expanding into. The answer is nothing. The universe is not expanding into anything. The universe is all of space. There is no outside. The balloon analogy uses a two-dimensional surface to represent our three-dimensional space, and that two-dimensional surface needs a third dimension to curve in. But our actual three-dimensional space does not require a fourth spatial dimension to expand into. It simply expands. The distances between points increase. That is all expansion means. More space exists between objects than existed before. No external space is required. Cosmic expansion was discovered in the 1920s when Edwin Hubble measured the redshifts of distant galaxies. 4 decades after this discovery, astronomers assumed that expansion was slowing down. Gravity pulls all matter together.
The gravitational attraction between galaxies should act as a brake on expansion, gradually slowing the rate at which galaxies separate. The big question was whether there was enough matter in the universe for gravity to eventually halt expansion entirely and reverse it, causing everything to collapse back together in a big crunch, or whether expansion would continue forever but gradually slow to a crawl. Both scenarios assumed that gravity was winning, that expansion was decelerating. Then in 1998, two independent teams of astronomers studying distant supernovae discovered something impossible. Expansion was not slowing down, it was speeding up. The universe is expanding faster now than it was billions of years ago. This acceleration violates every intuition about how gravity should work. Something is pushing space apart, counteracting gravity, driving galaxies away from each other with increasing vigor. That something is dark energy, and it is the most mysterious substance in the universe. We do not know what dark energy is. We do not know where it comes from. We do not understand its properties beyond the observational fact that it exists and causes acceleration. Current measurements suggest that dark energy makes up about 68% of the total energy density of the universe. Dark matter, the invisible substance that provides the gravitational scaffolding for galaxy formation, accounts for about 27%. Ordinary matter, the atoms that make up stars, planets, and everything we can see and touch, constitutes a mere 5%. We live in a universe dominated by things we do not understand, and the dominant component, dark energy, is actively tearing the cosmos apart. Dark energy behaves like anti-gravity, but that description is somewhat misleading. Gravity attracts. It pulls things together. Dark energy does not repel in the same way. Instead, it has a property that causes space itself to expand. The more space you have, the more dark energy you get. Because dark energy is a property of space itself. It has a constant energy density per unit volume. As space expands and volume increases, the total amount of dark energy increases. This creates a runaway effect. More space means more dark energy. More dark energy means faster expansion. Faster expansion creates even more space, which brings even more dark energy, which drives even faster expansion. The process accelerates. A billion years ago, expansion was slower than it is today. A billion years from now, expansion will be faster than it is today. The acceleration is relentless and increasing. Every second, the distance between distant galaxies increases by thousands of miles, not because the galaxies are moving, but because the space between them is growing. Consider two galaxies separated by a billion light years. In the time it takes you to read this sentence, the space between those galaxies has expanded by hundreds of thousands of miles. By tomorrow, millions of miles of new space
will exist between them. In a year, trillions of miles. The numbers are staggering and they grow larger every moment as acceleration continues. Every second, space expands. Every second, distances increase. The universe is being ripped apart from within, not by any external force, but by the properties of space itself. Think about what this means on the largest scales. Galaxy clusters, enormous collections of hundreds or thousands of galaxies bound together by gravity, are the largest gravitationally bound structures in the universe. Within a cluster, galaxies orbit each other. Gravity holds them together. Expansion cannot tear apart a galaxy cluster because local gravity is stronger than the expansion of space on those scales. But beyond galaxy clusters, gravity becomes too weak. Superclusters, vast chains and sheets of galaxy clusters spanning hundreds of millions of light years are not bound. They are being pulled apart. Different regions of a supercluster are receding from each other. In the distant future, these superclusters will be completely dispersed, their component clusters separated by such vast distances that they will lose all gravitational connection. On the very largest scales, expansion dominates completely. The cosmic web, the filamentary structure of matter that spans the observable universe, is being stretched. Voids are growing larger, filaments are becoming more elongated and tenuous, the universe is becoming less dense, more spread out, more empty. And this process is accelerating. We have direct evidence that space has been expanding for the entire history of the universe. The single most powerful piece of evidence is the cosmic microwave background radiation, the CMB. This is light that has been traveling through space for more than 13.8 billion years. It was emitted when the universe was only about 380,000 years old, during an epoch called recombination. Before recombination, the universe was so hot and dense that atoms could not form. Electrons and protons existed as a plasma, and this plasma was opaque to light. Photons could not travel far before being absorbed or scattered. Then the universe expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the universe became transparent. Light could travel freely. The photons that were released at this moment have been traveling through space ever since, and we detect them today as the cosmic microwave background. When these photons were emitted, they were high energy, visible light photons. The universe was hot, glowing at a temperature of about 3000 degrees Kelvin. But during the 13.8 billion years these photons have been traveling, space has been expanding the entire time. This expansion stretched the wavelengths of the photons. What started as visible light, orange and red photons, has been stretched into microwave radiation. The wavelength of this light has been increased by a factor of about 1100. The light has been redshifted by more than 3 orders of magnitude. Today, the CMB has a temperature of only 2.7 degrees Kelvin, just barely above absolute zero. This extreme redshift is direct, undeniable proof that space has expanded by a factor of about 1100 since the CMB was emitted. The universe is 1100 times larger now than it was then. Redshift is the key to understanding cosmic expansion and measuring distances in the universe. When an object is moving away from you, the light it emits gets shifted to longer wavelengths. This is called the Doppler effect, and it happens with sound waves too. An ambulance siren sounds higher pitched as it approaches and lower pitched as it recedes, because the sound waves are compressed or stretched by the ambulance's motion. Light works the same way. An object moving toward you emits light that is shifted to shorter, bluer wavelengths. An object moving away emits light shifted to longer, reader wavelengths. But there is a critical difference between Doppler shift caused by motion through space and cosmological redshift caused by the expansion of space. Doppler shift is caused by the relative velocity of the source and observer through space. Cosmological redshift is caused by the stretching of space itself during the light's journey. For nearby galaxies, the distinction does not matter much. Both effects produce similar redshifts. But for distant galaxies, the difference becomes crucial. A galaxy with a cosmological redshift of 2 has had its light stretched by a factor of 3 because space has expanded by a factor of 3 during the light's journey. This is not because the galaxy is moving away at some enormous velocity, it is because space itself has grown. The photon's wavelength stretched along with space. As space expanded, the photon expanded with it. This is why we can observe galaxies with redshifts that correspond to recession velocities faster than light. They are not moving faster than light through space. The space between us and them has simply expanded so much that the effective recession velocity exceeds light speed. Cosmologists use redshift to measure distances and map the history of the universe. A galaxy with redshift 1 is observed as it was when the universe was about half its current size. A galaxy with redshift 2 is seen when the universe was one-third its current size. A galaxy with redshift 10 is seen when the universe was only 1/11th its current size, in its infancy, less than a billion years after the Big Bang. The highest redshift galaxies observed by the James Webb Space Telescope have redshifts around 13 or 14, showing us the universe when it was only a few hundred million years old, when the first galaxies were just beginning to form. These extremely high redshift objects are incredibly distant. Their light has been traveling for more than 13 billion years. But due to expansion during that time, these galaxies are now more than 30 billion light years away from us in co-moving distance. We see them as they were in the distant past, tiny and young. Today, they are massive, mature galaxies, but we cannot see their current state. The light showing their current appearance will not reach us for billions more years, and by then, expansion may have carried them so far that their light becomes undetectable. We are racing against cosmic expansion, trying to observe as much as we can before it is too late. There is a boundary beyond which we can never send a signal that will be received. This is the cosmic event horizon, and understanding it requires careful thought. Imagine we send a beam of light toward a distant galaxy. The light travels at light speed, obviously, but the galaxy is receding because space between us and it is expanding. If the galaxy is close enough, the light will eventually catch up and reach it, even though the galaxy is moving away. The light is traveling faster than the recession velocity, so it makes net progress and eventually arrives. But if the galaxy is far enough away that its recession velocity exceeds the speed of light, the light we send cannot catch up. The light moves forward at light speed, but the space ahead of it is expanding faster than it can cover the distance. The light makes no progress toward the galaxy. It is stuck, frozen in space, running forward but getting nowhere. The galaxy we aimed at continues to recede, and our light beam, despite traveling at the ultimate cosmic speed, will never reach it. This defines the event horizon. Galaxies beyond this horizon are causally disconnected from us. No signal we send can reach them. No signal they send can reach us. We cannot communicate, we cannot interact, we cannot affect each other in any way. The event horizon marks the boundary of the region of space with which we can ever have causal contact. Where is this event horizon? The calculation is complex because it depends on the expansion rate, the acceleration of expansion, and the properties of dark energy. Current estimates place the cosmic event horizon at approximately 16 billion light years in co-moving distance. This is significantly closer than the edge of the observable universe at 46 billion light years. Wait, how can the event horizon be closer than the observable universe boundary? The observable universe includes everything from which light has reached us. The event horizon marks everything we could ever reach or signal. These are different things. We can observe galaxies from which light was emitted billions of years ago when they were closer to us. That light has reached us, so we can see those galaxies. But those same galaxies have now been carried by expansion to distances beyond the event horizon. They are currently receding faster than light. We can see their past, but we cannot affect their future. A signal sent to them now will never arrive. This creates a strange situation where we can observe many galaxies that we can never reach or communicate with. We are seeing ghosts, images
of objects that are now forever beyond our influence. The observable universe is larger than the reachable universe. We can see farther than we can travel or signal. This makes the prison walls even more confining. Every day, galaxies cross the event horizon. Every day, space expands enough that another galaxy slips beyond the point of no return. These galaxies do not vanish instantly. We continue to observe them for a very long time, watching increasingly outdated images as light from their past continues to arrive. But no new information from beyond the crossing point will ever reach us. We will never see what happens to those galaxies after they cross the horizon. They are lost to us, not destroyed, but removed from the portion of the universe with which we can interact. And this loss is accelerating. As dark energy continues to drive faster and faster expansion, the event horizon is effectively shrinking. More galaxies are crossing it, fewer galaxies remain within reach. Our prison is getting smaller, the walls are closing in. In the distant future, billions of years from now, only our local group of gravitationally bound galaxies will remain within the reachable universe. Everything else will have been carried beyond the event horizon. The universe will appear to be emptying out, becoming darker and more isolated. Future astronomers will live in a cosmos far lonelier than the one we observe today. This is not a wall we can break through with better technology. This is not a temporary limitation that clever engineering will overcome. This is a fundamental barrier imposed by the structure of space-time and the properties of cosmic expansion. You cannot build a faster ship because nothing goes faster than light. You cannot find a shortcut because space itself is expanding everywhere. You cannot wait for the wall to move because it is moving toward us, not away. Every idea for escaping this prison fails when confronted with the reality of accelerating cosmic expansion. Warp drives, wormholes, hyperspace, every science fiction dream collides with the immovable fact that space is stretching faster than anything can cross it. The expansion is not something happening in space. It is something happening to space. You cannot outrun the racetrack when the racetrack itself is stretching faster than you can run. This is our reality. Space is stretching, galaxies are being carried away, the event horizon is shrinking. We are trapped in an increasingly small region of causally connected space, watching the rest of the universe recede beyond reach. And there is absolutely nothing we can do about it. The walls of our cosmic prison are made of expanding space itself, and those walls are unbreakable. We have explored why light speed creates a limit and how cosmic expansion creates a barrier. Now we must confront what we are losing and can never recover. The universe is disappearing before our eyes. Right now, at this very moment, galaxies are slipping beyond
the cosmic horizon, crossing the event horizon from which no signal can return, vanishing from the portion of reality we can ever observe or interact with. This is not a slow process happening on incomprehensible timescales. This is happening now, today, continuously. Every second that passes, space expands. Every second, distant galaxies are carried a bit farther away. Every day, thousands of galaxies cross the threshold and become permanently unreachable. This is an ongoing cosmic tragedy, a relentless loss of access to the universe itself. We are watching the cosmos drain away. watching reality shrink around us, watching our prison walls close in, and we can do nothing to stop it. The galaxies are not being destroyed. They continue to exist, continue to form new stars, continue their evolution, but they might as well not exist for all the difference it makes to us. They are gone, removed from our reality, expelled from the observable universe into the realm of the forever inaccessible. This is what cosmic expansion steals from us, not matter or energy, but possibility itself. The possibility of ever knowing what lies beyond, the possibility of ever reaching distant shores, the possibility of ever making contact with whatever or whoever might exist out there in the vast expanse we will never see. The boundary that determines what we are losing is called the Hubble sphere. This is the distance at which the recession velocity of space equals the speed of light. Remember Hubble's law. The farther away a galaxy is, the faster it recedes due to cosmic expansion. At a certain distance, roughly 14 billion light years in current conditions, galaxies are receding at exactly light speed. Closer than this distance, galaxies recede slower than light. We can send signals to them. Light we emit will eventually reach them, though it may take billions of years. Farther than this distance, galaxies recede faster than light. Light we send toward them cannot catch up. The space between us and them is expanding too rapidly. Our light makes no forward progress. Now, the Hubble sphere is not the same as the cosmic event horizon, but it is related. The event horizon, at about 16 billion light years, marks the boundary beyond which we can never send a signal that will arrive. The Hubble sphere marks where recession velocity equals light speed. Galaxies can cross the Hubble sphere in either direction. In fact, some of the galaxies we observe today are beyond the Hubble sphere, receding faster than light. We can see them because the light we detect was emitted long ago when they were closer inside the Hubble sphere. That ancient light has been traveling toward us for billions of years and has finally arrived, but those same galaxies are now receding faster than light, beyond our ability to ever signal or reach. The light we see is the last we will ever receive from beyond a certain point in their history. How many galaxies are we losing? The numbers are staggering and depressing. Current estimates suggest the observable universe contains approximately 2 trillion galaxies. 2 trillion separate island universes, each containing hundreds of billions of stars, each star potentially hosting planets, each planet potentially harboring conditions for life. This is the census of what we can observe right now. But the majority of these 2 trillion galaxies are already beyond our event horizon. We can see them, but we cannot reach them. They have already been carried by expansion to distances from which they can never be recovered, and every moment more galaxies cross over. Calculating the exact rate of loss requires detailed cosmological modeling accounting for the expansion rate, the acceleration of expansion, and the distribution of galaxies across space. Different models give slightly different numbers, but the general conclusion is consistent. We are losing access to billions of galaxies every million years. Not losing in the sense of their light fading from our telescopes, that happens much more slowly. Losing in the sense that they cross the event horizon and become forever unreachable. A million years is nothing on cosmic timescales. In the time since early humans first stood upright, we have lost access to billions of galaxies. In the time since the dinosaurs went extinct, we have lost access to trillions. The loss is accelerating along with the expansion. Dark energy grows stronger over time as more space creates more dark energy. The rate at which galaxies slip away increases. We are hemorrhaging access to the universe at an ever growing pace. 2 trillion galaxies sounds like an enormous number, and it is. Each galaxy contains on average about 100 billion stars. Some galaxies are smaller, dwarf galaxies with only a few million stars. Some are giants with a trillion stars or more. Averaging across all galaxies gives us about 100 billion stars per galaxy. Multiply 2 trillion galaxies by 100 billion stars per galaxy, and you get 200 billion trillion stars in the observable universe. That is a 2 followed by 23 zeros, 200 sextillion stars. each one a sun, potentially with planets, potentially with moons, potentially with environments where chemistry could become biology. The number of possible sites for life is almost incomprehensibly large, and yet this enormous number represents only what we can observe. If the universe is infinite, and many cosmologists believe it is, then our observable bubble of 2 trillion galaxies represents exactly 0% of everything that exists. Infinity is strange. Any finite number, no matter how large, is infinitesimally small compared to infinity, 0%. All the galaxies we can see, all the stars, all the planets, all the potential life, all the civilizations that might exist within our observable universe, all of it together is 0% of an infinite cosmos. The universe beyond our horizon of infinite
contains infinite galaxies, infinite stars, infinite planets, infinite possibilities. And we can see none of it. We are trapped observing a finite sample of an infinite reality, forever cut off from the rest. Even if the universe is not infinite, even if it is merely vastly larger than our observable region, the implications are humbling. Cosmological models based on observations of the cosmic microwave background suggest that if the universe is finite, it is at least 250 times larger than the observable universe in volume. Our bubble would be a tiny fraction of the whole, less than 1/10 of 1%. Most of reality lies beyond our horizon. Most of the universe is invisible to us, unreachable, unknowable. We exist in profound cosmic isolation, able to observe and interact with only a tiny sliver of everything that is. This isolation becomes even more poignant when we consider the possibility of other civilizations. Are we alone in the universe? This is one of humanity's deepest questions. We search for signals from alien civilizations. We listen for radio transmissions, look for artificial structures, analyze exoplanet atmospheres for biosignatures. So far, we have found nothing. The universe seems silent, empty of other intelligence. But what if we are looking in the wrong place? What if advanced civilizations exist or existed in galaxies that are now beyond our cosmic horizon? What if, billions of years ago, when the universe was smaller and everything was closer together, thousands or millions of civilizations arose, built societies, transmitted signals, lived and thrived in galaxies that are now receding from us faster than light? Those civilizations, if they existed, are lost to us forever. We will never receive their signals because those signals cannot cross the expanding space between us. We will never know they were there. We will never learn about their science, their culture, their history. They might be looking for us, transmitting powerful beacons, hoping to make contact, but their signals are trapped, frozen in expanding space, running toward us at light speed, but making no net progress because space expands faster. Our signals suffer the same fate in reverse. We transmit radio waves into space, hoping someone might hear us, but any signal we send to a galaxy beyond the event horizon will never arrive. It will travel outward forever at light speed, never reaching its destination, never making contact. This is cosmic loneliness on the grandest scale. Imagine intelligent beings on a planet orbiting a star in a galaxy now 20 billion light years away. They evolved, became conscious, built civilizations, wondered if they were alone, searched the skies for signs of other life. They exist right now at this very moment. But we can never know about them. They can never know about us. The expanding universe has placed us in separate bubbles of causality. We share the same cosmos, but we exist in mutually inaccessible regions of it. The distance is not the problem. The problem is that the space between us is expanding faster than any signal can cross. We are separated not by distance, but by the dynamics of space-time itself. This represents a form of information loss that troubles physicists deeply. Information, in the physics sense, is anything that can be known, measured, or observed. The state of a system, the history of events, the properties of objects. All of this is information. In most contexts, information cannot be destroyed. It can be scrambled, hidden, or transformed, but it still exists somewhere in principle. This is related to fundamental symmetries in physics and the reversibility of physical laws. But cosmic expansion appears to destroy information by making it permanently inaccessible. A galaxy that crosses beyond our cosmic horizon takes all of its information with it. Everything about that galaxy, its structure, its history, the events occurring within it becomes unknowable. We cannot retrieve that information, we cannot reconstruct it, we cannot infer it indirectly. It is simply gone from our accessible reality. Physicists have debated whether this represents true information destruction or merely information hiding. The information still exists in some abstract sense. The galaxy is still out there, still real, still obeying physical laws. But if information is fundamentally inaccessible, if no experiment or observation could ever retrieve it, does it matter whether it technically exists? For all practical purposes, the information is destroyed. This connects to deep questions about the nature of reality, observation, and existence. If something exists but cannot be observed, even in principle, in what sense does it exist for us? The isolation gets worse over time, much worse. Current observations show that we live in a universe dominated by dark energy, and dark energy appears to have a constant density per unit volume. As space expands, more dark energy comes into existence, driving faster expansion, creating even more space and even more dark energy. This runaway process means that expansion accelerates indefinitely into the future. Barring some unexpected change in the properties of dark energy, the universe will expand faster and faster forever. In approximately 150 billion years, something dramatic will happen. Every galaxy outside our local gravitationally bound group will have been carried beyond the cosmic horizon. Andromeda, the Milky Way, Triangulum, and our few dozen satellite dwarf galaxies will have merged into one massive elliptical galaxy. This merged galaxy will be all that remains visible. Beyond it, in every direction, the universe will appear completely empty. Dark, void, not a single external galaxy will be observable. Future astronomers living in that era will look out at the cosmos and see nothing but their own galaxy surrounded by darkness. They will have no evidence that billions of other galaxies ever existed. The rich tapestry of cosmic structure that we observe today, the galaxy clusters, the cosmic web, the large-scale structure of matter, all of it will have been carried beyond the horizon, faded from view, erased from the observable universe. But the loss extends beyond galaxies. Even the cosmic microwave background radiation, the most ancient light in the universe and our best evidence for the Big Bang, will eventually disappear. The CMB is already incredibly redshifted, stretched from visible light to microwave radiation by cosmic expansion. But expansion continues. The wavelength of the CMB photons continues to increase. In the far future, the CMB will be redshifted into long-wave radio, then into wavelengths longer than the size of galaxies, longer than the size of galaxy clusters, longer than any reasonable detector could measure. The ZMB will effectively vanish, its energy density diluted to undetectability. Future scientists will lose the primary evidence that allowed us to understand the Big Bang, cosmic inflation, and the early history of the universe. They will lack the data needed to reconstruct how the universe began. They might develop theories, but they will have no observational evidence to confirm or refute those theories. They will be blind to cosmic history, living in a present disconnected from any knowable past. Their observable universe will consist of a single galaxy in an apparently infinite void with no evidence of expansion, no evidence of a beginning, no evidence of the vast cosmos that existed when the universe was younger. They will be far more isolated, far more ignorant of reality than we are. This future scenario is not speculation. It is the inevitable outcome of accelerating expansion driven by dark energy with constant density. The math is clear, the physics is well understood. Unless something unexpected changes the properties of dark energy, this is our universe's future, a slow fade into darkness and isolation. Astronomers in that distant era might conclude that the universe is static, eternal, and consists only of their single merged galaxy. They would be wrong, but they would have no way to know they are wrong. The evidence of a larger cosmos will have been erased by expansion. We live in a privileged era, a temporary window when the universe is old enough to have formed rich structure but young enough that most of that structure remains observable. Past epochs were less interesting, dominated by simpler, younger structures. Future epochs will be more isolated with less accessible structure. We exist at a special time, cosmologically speaking, and that time is ending. The window is closing. Every day, a bit more of the universe slips away into permanent inaccessibility. We have already lost vast regions of space. This is not just a future problem, it is happening now and has been happening throughout cosmic history. In the early universe, when everything was much closer,
together, many regions of space were within causal contact with each other. Signals could propagate between them, information could be exchanged, but as the universe expanded and expansion accelerated, regions that were once in contact became separated. Space expanded between them faster than light could cross. They became causally disconnected. What was once one connected region of space became many separate bubbles of causality, each forever isolated from the others.
our observable universe is one such bubble. There are regions of space that were once close enough to affect the region that would become our observable universe. Those regions contributed to the initial conditions, the density fluctuations, the quantum variations that eventually form the structures we see. But those same regions are now tens of billions of light years away, far beyond our cosmic horizon, receding faster than light. We evolved from initial conditions that were influenced by regions we can never observe. We are the product of a larger cosmos that is now mostly inaccessible to us. Our past was shaped by places we cannot see. Our future will be shaped by the ongoing loss of access to more and more of reality. Consider the scale of what we are losing. Every galaxy contains hundreds of billions of stars. Every star is a nuclear furnace, converting hydrogen into heavier elements, shining for billions of years. Many stars have planets. Some of those planets are in habitable zones where liquid water can exist. Some percentage of those planets developed life. We do not know what percentage, but even if life is rare, the numbers are so large that even a tiny fraction implies countless living worlds. Some of those worlds might have evolved intelligence, some might have developed technology, some might have built civilizations that lasted millions of years, civilizations that explored their star systems, that wondered about their place in the cosmos, that searched for others like them. All of this might have happened, might be happening right now in galaxies beyond our horizon, and we will never know. They will never know about us. We are separated by expanding space, each trapped in our own bubble of observability, each living out our existence in cosmic isolation. The tragedy is not that we are alone. The tragedy is that we might not be alone, but we are separated by barriers we cannot overcome. The universe might be teeming with life, with intelligence, with civilizations, but they are scattered across separate, causally disconnected regions of space. Each species, each civilization trapped in their own prison, wondering if they are alone, never knowing that countless others exist just beyond reach. This is what we are losing, not just galaxies, not just stars, but possibility. The possibility of knowledge, of contact, of understanding what lies beyond. We are losing the ability to answer fundamental questions. Is life common or rare? Does intelligence arise inevitably?
Or is it a cosmic accident? Are there civilizations older and wiser than ours? Have others solved problems we struggle with? What diversity of life and mind exists in the cosmos? We are losing the ability to answer these questions because we are losing access to the data. The answers exist out there in those distant galaxies, but those galaxies are receding beyond the event horizon. The information is leaving our universe, our observable universe, and taking the answers with it. We live in a cosmos that is actively erasing itself from our view, destroying its own legibility, making itself unknowable. The walls of our prison are not static, they are closing in, squeezing our bubble of observability smaller and smaller. We are losing the universe, losing access to reality itself, losing the chance to ever know what truly exists beyond the walls. And there is nothing, absolutely nothing, that we can do to prevent it. The loss is permanent, absolute, and accelerating. This is the price of living in an expanding universe dominated by dark energy. We pay that price in lost knowledge, lost possibilities, lost cosmic companionship. The universe is disappearing and we can only watch it go. The cosmic horizon is not a wall, not in any conventional sense. There is no surface you could touch, no barrier you could see, no physical structure marking the boundary. If you could somehow travel toward the horizon, you would pass through the location where it appears to be without encountering anything. The horizon would simply recede before you, always staying the same distance ahead, always out of reach. This is because the cosmic horizon is not a thing. It is a boundary in space-time itself, a geometric limit defined by the relationship between light speed, the age of the universe, and the expansion of space. It is more like the horizon you see when standing on Earth's surface, the line where the sky appears to meet the ground. That horizon is not a physical object, it is a limitation of your perspective, a consequence of standing on a curved surface and having a finite range of vision. Walk toward the horizon on Earth and it moves with you, always staying at the same apparent distance. The cosmic horizon works similarly, but instead of being created by the curvature of Earth's surface, it is created by the structure of space-time and the finite age of the universe. You cannot reach it because it is not a place, it is a limit on what can be observed from any given location. Cosmologists use technical terminology to distinguish between different types of horizons, and understanding these distinctions is crucial to understanding our cosmic prison. The first and most important is the particle horizon. This is the boundary of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang. The name comes from the fact that this horizon marks the limit of which particles we can theoretically have interacted with or received signals from. Any particle beyond the particle horizon exists in a region of space that has never been in causal contact with our region. The light or signals from those particles have not had sufficient time to travel to us. Um, the particle horizon is located at approximately 46 billion light years in co-moving distance, accounting for the expansion of space during the time the light has been traveling. This boundary represents everything we can see, everything we can measure, everything we can observe about the universe. Beyond the particle horizon lies the unobservable universe, regions of space that might as well not exist from our perspective because we can never detect them. The particle horizon grows over time. Every second, light from slightly more distant regions has time to reach us, expanding our observable bubble by approximately one light second. But this growth is deceptive because while we are gaining access to previously unobservable regions, we are simultaneously losing access to regions that are crossing the event horizon. The event horizon is different from the particle horizon, and the distinction is critical. The particle horizon marks what we can see right now based on light that has already reached us. The event horizon marks what we can ever affect or communicate with in the future. More precisely, the event horizon is the boundary beyond which events happening now can never be observed by us no matter how long we wait. A galaxy beyond the event horizon is receding so rapidly that light emitted from it right now will never reach us. The space between us and that galaxy is expanding faster than the light can cross it. Even if we wait trillions of years, that light will never arrive. The event horizon in an expanding universe is analogous to the event horizon of a black hole, though the physics is inverted. Around a black hole, anything crossing the event horizon cannot escape because space is falling into the black hole faster than light
can climb out. In our expanding universe, anything beyond the cosmic event horizon cannot reach us because space is expanding faster than light can cross it. The event horizon is located at approximately 16 billion light years in co-moving distance, much closer than the particle horizon. This means we can observe many galaxies that we can never signal or travel to because they have already crossed the event horizon even though their ancient light is still arriving. We see their past but cannot affect their future. The event horizon does not grow over time. In fact, due to accelerating expansion, it is effectively shrinking. More galaxies are crossing it. Fewer regions remain within our sphere of possible influence. Here is a concept that breaks most people's intuition about cosmic horizons. Every observer in the universe has their own unique cosmic horizon centered on their location. There is no universal edge, there is no absolute boundary. The horizons are observer dependent. And you have your cosmic horizon. An alien on a planet in the Andromeda galaxy has their cosmic horizon centered on them. The two horizons are slightly different, offset by the 2.5 million light years separating us. An alien in a galaxy 10 billion light years away has their cosmic horizon, and it overlaps with ours only partially. Some of what they can observe, we cannot. Some of what we can observe, they cannot. This creates a bizarre situation where the universe is carved up into overlapping bubbles of observability, each bubble centered on a different observer. No observer can see everything. Each observer sees a different sample of the total cosmos. If the universe is infinite, then there are infinite observers, each with their own finite observable bubble, each bubble containing a different 46 billion light-year radius sphere of space. Most of these bubbles do not overlap at all. Most observers in an infinite universe are so far apart that their observable bubbles are completely separate, disjoint, causally disconnected. Those observers live in effectively separate universes even though they technically inhabit the same spacetime. Consider an observer at the edge of our observable universe, a civilization on a planet in a galaxy 46 billion light years away. From our perspective, that galaxy is at the limit of what we can observe. It sits right on our particle horizon, but from the perspective of an observer in that galaxy, we are at the edge of their observable universe. They have their own 46 billion light-year radius bubble of observability centered on their location. Their bubble extends in all directions around them, including directions away from us. In the direction away from us, their bubble extends another 46 billion light-years beyond their position. That means they can observe regions of space that are 92 billion light-years away from us, regions that are far, far beyond our particle horizon. Those regions exist, but we cannot observe them and never will. The observer in that distant galaxy can see both us and those far regions. They exist in an overlapping zone, able to observe a portion of what we see and a portion of what we cannot. They are a cosmic intermediary, able to observe both sides of a divide that we cannot cross. Now imagine an observer in one of those far regions 92 billion light years from us. They have their own observable bubble. They can see the intermediary galaxy but cannot see us. We exist beyond their particle horizon just as they exist beyond ours. The universe is a vast network of overlapping observable bubbles, each observer able to see some things but not others, each bubble offset from the next, creating a patchwork of partial observability that covers the cosmos. This raises questions about the structure of space beyond our horizon. What does it look like out there? Is it similar to what we observe within our bubble? Or does it differ in some fundamental way? Cosmologists have strong reasons to believe that the universe beyond our horizon resembles the universe within it. The evidence comes from observations of the cosmic web, the large-scale structure of matter in the universe. On scales of hundreds of millions of light years, matter is not distributed uniformly. It clumps into filaments, sheets, and clusters with enormous voids in between. This structure looks like a cosmic web or foam with galaxies concentrated along the filaments and in the nodes where filaments intersect. This structure extends across the entire observable universe. Wherever we look, we see similar patterns. The cosmic web appears uniform in its statistical properties. Different regions show the same types of structures at the same scales. When we look toward the edge of our observable universe near the particle horizon, we see the same cosmic web structure we see nearby. The filaments, clusters, and voids extend right up to the horizon and presumably continue beyond it. There is no evidence of any change in structure as we approach the horizon. The universe does not become different or strange at the edge of observability. It simply continues. This uniformity is predicted by the cosmological principle, one of the fundamental assumptions underlying modern cosmology. The cosmological principle states that the universe is homogeneous and isotropic on large scales. Homogeneous means the same everywhere. Isotropic means the same in all directions. Observations support this principle. The universe looks statistically identical, whether we look north, south, east, west, up, or down. No direction is special. The distribution of galaxies, the temperature of the cosmic microwave background, the expansion rate, all these properties appear uniform across the sky. The uniformity suggests that the universe has no center and no edge. Every location is equivalent. What we observe here is representative of what exists everywhere else. If the cosmological principle holds beyond our observable universe, and most cosmologists believe it does, then the universe beyond our particle horizon is just more of the same. More cosmic web structure, more galaxies arranged in filaments and clusters, more stars, more planets, more of everything. The unobservable universe is not a different realm with alien physics. It is simply more space we cannot see, filled with structures similar to those we can observe. This is both comforting and humbling. Comforting because it means we probably understand the general nature of the entire universe, even though we can only observe a small part of it. Humbling because it emphasizes how small our observable sample is compared to the whole. But there is one horizon that represents an actual impenetrable barrier beyond which we cannot see even in principle. This is the surface of last scattering, the cosmic microwave background itself. The Yambi is not just the oldest light we can detect. It is the oldest light that all can exist as free electromagnetic radiation traveling through space. Before the CMB was emitted, the universe was opaque. The cosmic microwave background represents the moment when the universe became transparent, and that moment creates an absolute barrier to observation. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Temperatures exceeded 10,000 degrees Kelvin. At these temperatures, electrons and protons could not bind together to form neutral atoms. Free electrons filled all of space, and these free electrons interacted constantly with photons. A photon could not travel far before being absorbed or scattered by an electron. Light was trapped, constantly absorbed, and re-emitted, unable to propagate freely. The universe was opaque, like being inside a dense fog where you cannot see more than a few inches. This epoch is called the photon epoch or the plasma epoch. No observation can penetrate it because light from earlier times cannot reach us. It was absorbed and rescattered in the plasma. Then, about 380,000 years after the Big Bang, the universe expanded and cooled enough for a critical transition to occur. The temperature dropped below about 3000 degrees Kelvin. At this temperature, electrons and protons could finally combine to form neutral hydrogen atoms. This process is called recombination, though the name is misleading because electrons and protons were combining for the first time, not recombining. Once neutral atoms formed, the free electron density dropped dramatically. Photons could travel freely without being absorbed or scattered. The universe became transparent. The photons that were released at this moment when the fog cleared have been traveling through space ever since. They are the cosmic microwave background radiation we detect today. The moment of recombination defines a surface in space-time called the surface of last scattering. This is the last surface from which photons scattered before the universe became transparent. It is the farthest back in time we can see using light. Beyond the surface, the universe is opaque. We cannot see earlier times because light from earlier times was trapped in the plasma and never escaped. The surface of last scattering surrounds us at a distance of about 46 billion light years, coinciding with the particle horizon. It forms a spherical shell around us, the edge of the observable universe in time as well as space. This is a true barrier, not just a limit on how far light has traveled, but a limit on how far light can ever travel from the early universe. The surface of last scattering is not a physical surface. No material exists there now. It is a surface in space-time, a moment in cosmic history. When we observe the CMB, we are seeing light that has been traveling for 13.8 billion years. That light was emitted from regions of space that are now 46 billion light years away due to expansion. We are looking back in time to when those regions were much closer, when the universe was much smaller and denser, when the temperature everywhere was 3000 degrees and atoms were just beginning to form. Different parts of the CMB sky show us different regions of space at that early moment. The entire observable universe at the moment of recombination is projected onto the sky as the CMB. It is like a cosmic photograph, a snapshot of the universe at age 380,000 years. We can analyze this snapshot in incredible detail, measuring tiny temperature fluctuations, studying the statistical properties of those fluctuations, learning about the initial conditions that led to the structures we see today. But we cannot see beyond it. The surface of last scattering is the ultimate wall, the final barrier, the absolute limit of electromagnetic observation. Behind it lies the Dark Age, the plasma epoch, the inaccessible early universe. Some physicists have speculated about what happens at the very edge of spacetime, at the absolute boundary of the observable universe. Does spacetime remain smooth and continuous right up to the horizon, or does something strange occur? At extremely small scales, far below anything we can currently observe, quantum mechanics suggests that spacetime itself might not be smooth. There might be quantum fluctuations in the geometry of space, a foaming, bubbling structure at the Planck scale, about 10 to the negative 35 meters. This quantum foam is predicted by attempts to unify quantum mechanics and general relativity, though we have no direct evidence for it. If quantum foam exists, it is far too small to observe directly. But some theories suggest that near cosmological horizons, quantum effects might become amplified or observable in indirect ways. The event horizon of a black hole is known to have quantum properties, most famously Hawking radiation, where quantum fluctuations near the horizon produce pairs of particles, one falling into the black hole and one escaping. Could something similar happen at the cosmic event horizon? Could quantum fluctuations near the boundary between the observable and unobservable universe produce detectable effects? Most physicists think not. The cosmic event horizon is very different from a black hole event horizon. It is not a local feature of space-time, but a global consequence of expansion. There is nothing special about the local geometry of space at the cosmic horizon. An observer passing through their own cosmic event horizon would notice nothing unusual. Space would appear smooth and normal. Only later, looking back, would they realize they had crossed the boundary from which signals could no longer return to their origin point. The horizon is not in any particular location, it is a relationship between different regions of space-time. Still, the horizon represents a fundamental limitation on knowledge and observation. It carves the universe into separate domains of causality. Events on opposite sides of an event horizon cannot influence each other. They are, for all physical purposes, in separate universes. This has led some physicists to wonder whether the concept of a single universe even makes sense in the presence of cosmic horizons. If we can never observe or interact with regions beyond our horizon, in what sense do those regions belong to the same universe as us? This is not just philosophy, it connects to deep questions in quantum mechanics about the role of observation and measurement. Does something exist if it is fundamentally unobservable? Does a galaxy beyond our horizon exist in the same sense as a galaxy we can see? These questions remain unresolved, touching on the interpretation of quantum mechanics, the nature of reality, and the relationship between existence and observation. What is clear is that the cosmic horizon divides spacetime into separate causal domains. We live in one such domain, able to observe and interact with a finite region centered on us. Beyond that region lies more spacetime, more events, more structure, but it is forever separated from us by the expansion of space. The wall is not made of matter or energy, it is made of geometry and causality, and that makes it unbreakable. The structure of the wall, if we can call it that, is the structure of space-time itself under expansion. It is not a thing but a boundary, not a location but a limit, not an obstacle but a consequence of fundamental physics. Understanding this structure helps clarify why escape is impossible. You cannot break through the wall because there is nothing to break through. You cannot go around it because it surrounds you in all directions. You cannot wait for it to move because it is defined by the causal structure of spacetime, and that structure is absolute. The wall is the edge of what can be known, the boundary of what can be experienced, the limit of reality itself as far as observation is concerned. And now that we understand its structure, we must confront the desperate question that arises naturally. If this is the wall that confines us, can we find any way through? Can any technology, any physics, any cleverness allow us to breach this barrier and reach what lies beyond? The answer will test the limits of known physics and force us to confront the possibility that some boundaries truly cannot be crossed. Science fiction offers us dreams of faster than light travel, warp drives that bend space around a starship, allowing it to effectively move faster than light without technically violating relativity. Wormholes that punch shortcuts through the fabric of space-time, connecting distant locations through tunnels that bypass the normal distances between them. Hyperspace, alternate dimensions, subspace, quantum tunneling across cosmic distances. These concepts dominate our stories about space exploration and galactic civilizations. They represent humanity's refusal to accept limitations, our insistence that sufficiently advanced technology can overcome any obstacle. But when we examine these ideas with rigorous physics, when we ask whether they could actually breach the cosmic horizon and allow us to reach galaxies beyond the event horizon, every single one fails. Not because we lack the engineering capability to build them, but because they violate fundamental principles of physics that cannot be circumvented. The cosmic prison is not locked by insufficient technology. It is locked by the laws of nature themselves. No key exists because the lock is made of mathematics and geometry. Let us examine each proposed escape method and understand exactly why it fails. The Alcubierre drive is the most scientifically serious proposal for faster than light travel. Proposed by physicist Miguel Alcubierre in 1994, it is based on a solution to Einstein's equations of general relativity. The concept is elegant. Instead of moving a spacecraft through space at faster than light speed, which relativity forbids, you warp the space around the spacecraft, you contract space in front of the ship and expand space behind it, creating a wave of space-time distortion that carries the ship forward. The spacecraft itself remains stationary within a bubble of flat spacetime and never moves faster than light relative to the space immediately around it. But the bubble moves, and the bubble can move faster than light because spacetime itself is not restricted to light speed. The ship surfs on a wave of warp space, potentially reaching speeds many times faster than light, as measured by an external observer. The mathematics works. The equations are consistent with general relativity. On paper, the Alcubierre drive does not violate any known laws of physics, but the practical and theoretical problems are insurmountable. First, creating the necessary space-time distortion requires matter or energy with negative mass or negative energy density. This is called exotic matter. Nothing like this has ever been observed. We have never detected any substance with negative energy density. Some quantum field effects, like the Casimir effect, involve regions of negative energy density on microscopic scales, but scaling this up to macroscopic levels seems impossible with any known physics. The amount of exotic matter required is staggering. Early calculations suggested you would need exotic matter with total mass energy equivalent to the entire observable universe just to create a warp bubble a few meters across. Later refinements reduced this estimate, but even optimistic calculations require exotic matter equivalent to the mass of Jupiter or more. And remember, this is not ordinary matter. This is matter with properties we have never observed and which may not exist. Even if we could somehow acquire exotic matter and build an Alcubierre drive, it would not help us breach the cosmic event horizon. Here is why. Sounds to me. Alcubierre drive allows you to move through space faster than light, but it does not allow you to outrun the expansion of space itself. If you aim your warp drive at a galaxy beyond the event horizon, a galaxy receding at faster than light due to cosmic expansion, you will make no progress toward it. The space between you and that galaxy is expanding faster than your warp drive can contract it. You are contracting space in front of you and expanding it behind you, but the overall expansion of the universe is expanding space everywhere, including the space you just contracted. It is like trying to run up a down escalator that is moving faster than you can run. You move your legs, you exert effort, but you make no net progress. The escalator carries you backward faster than you move forward. The expansion of space does the same thing to a warp drive trying to reach a galaxy beyond the event horizon. The drive might allow you to traverse space within the reachable universe more quickly, visiting galaxies that are within the event horizon but far away. But it cannot bridge the boundary. The mathematics of space-time expansion is more fundamental than the mathematics of the warp drive. The expansion wins. Wormholes represent another staple of science fiction, and like the Alcubierre drive, they are based on real solutions to Einstein's equations. A wormhole is a tunnel through space-time connecting two different locations. Instead of traveling the long way around through normal space, you enter one end of the wormhole and emerge from the other end, having crossed vast distances through a shortcut. The distance through the wormhole can be much shorter than the distance through normal space between the same 2 points. In principle, you could have a wormhole where the journey through the tunnel is only a few miles, even though the two mouths of the wormhole are separated by billions of light years in normal space. Einstein and Nathan Rosen described this possibility in 1935, and such structures are sometimes called Einstein-Rosen bridges. But naturally occurring wormholes, if they exist, are not traversable. They collapse too quickly for anything to pass through. Making a wormhole traversable requires holding it open with exotic matter, the same negative energy density material required for the Alcubierre drive. We face the same problem. We have never observed exotic matter and have no idea how to create or manipulate it in the quantities required, but assume we somehow solve this problem. Assume we can create and stabilize a traversable wormhole. Could we use it to reach a galaxy beyond the cosmic event horizon? The answer is no. Here is the fundamental issue. You cannot create a wormhole mouth at a location you cannot reach. To place one end of a wormhole at a distant location, you must first travel to that location through normal spacetime, or send some object or probe there that can establish the wormhole mouth. If a galaxy is beyond the cosmic event horizon, you cannot send anything there. No signal, no probe, no information can reach it. Therefore, you cannot establish a wormhole connection to it. Wormholes can only connect locations that are already causally connected. They can make the journey between those locations shorter, but they cannot connect locations that are causally disconnected by cosmic expansion. The expansion of spacetime itself prevents the establishment of a wormhole to regions beyond the event horizon. Even if a wormhole somehow already existed connecting us to a distant galaxy, if that galaxy crosses the event horizon due to expansion, The wormhole itself would be affected by the expansion. The throat of the wormhole would stretch along with space. The shortcut would get longer. Eventually, the wormhole would become as long as the normal spacetime distance between the 2 points, eliminating any advantage. Or the wormhole might become unstable and collapse as expansion stretches it beyond the limits that exotic matter can sustain. Wormholes do not allow us to escape the cosmic prison. They are limited by the same causal structure of spacetime that creates the prison in the first place. Every faster than light concept, every exotic propulsion system, every speculative technology faces the same fundamental barrier. No information transfer can exceed the speed of light in any local reference frame. This is not an engineering limitation, this is a consequence of the structure of space-time itself. Special relativity tells us that space and time are connected. Moving faster in space means moving slower in time. As you approach light speed, time dilation becomes extreme. Time passes more slowly for you relative to the outside universe. If you could reach light speed, time would stop for you entirely. Reaching faster than light speeds would require moving backward in time, which creates causality violations and paradoxes. You could receive messages before they were sent. You could arrive at your destination before you departed. The universe does not permit this. The speed of light is not just a speed limit for matter, it is the speed at which causality propagates. Cause and effect cannot be separated by a time-like interval shorter than light speed allows. This is baked into the geometry of spacetime. Any attempt to send information faster than light, by any means, would violate causality and create logical contradictions. The universe protects itself from these contradictions by making faster than light information transfer impossible. People often ask about quantum entanglement. If two particles are entangled, measuring one instantly affects the measurement outcome of the other, even if they are separated by vast distances. Does this not constitute faster than light communication? Could we use entangled particles to send messages to galaxies beyond the event horizon? The answer is no, and the reason is subtle but important. Quantum entanglement does involve a kind of instantaneous correlation between distant particles. When you measure an entangled particle and get a particular result, the other particle's measurement result is instantly determined, no matter how far away it is. This seems to suggest information traveling faster than light, but here is the catch. You cannot control what result you get when you measure your particle. The outcome is random. You cannot encode a message in your measurement results because you cannot determine what those results will be. The person measuring the distant particle also gets random results. Only when the two sets of results are brought together and compared do the correlations become apparent, and bringing the two sets of results together requires classical communication, which cannot exceed light speed. Quantum entanglement allows for correlations, but not for communication. No usable information transfers faster than light. The randomness of quantum measurements ensures that causality is preserved. You cannot use entanglement to breach the cosmic horizon. Even if we could somehow move faster than light, even if we could violate causality and break the fundamental structure of spacetime, we would still face an impossible challenge. Galaxies beyond the event horizon are receding at speeds far exceeding light speed. A galaxy at the event horizon recedes at exactly light speed. A galaxy twice as far recedes at twice light speed. A galaxy 3 times as far recedes at 3 times light speed. The farther beyond the horizon you look, the faster the recession. Galaxies near the edge of the observable universe, 46 billion light years away, are receding at speeds of 3 or 4 times the speed of light. To reach such a galaxy, you would need to travel not just faster than light, but 3 or 4 times faster than light, and you would need to sustain that speed for billions of years. The distance is so vast that even at these impossible speeds, the journey would take longer than the current age of the universe, and during that journey, space continues expanding. By the time you reach the location where the galaxy was when you started your journey, the galaxy would have been carried much farther away by ongoing expansion. Your destination recedes faster than you can pursue it. Consider a thought experiment. Suppose we had a spacecraft capable of traveling at the speed of light, and we aimed it at a galaxy that is currently within our observable universe but approaching the event horizon. The spacecraft begins its journey. It travels at light speed toward the target galaxy, but the galaxy is receding due to expansion. If the galaxy is close enough, closer than the event horizon, the spacecraft will eventually catch up and arrive. The journey will take longer than the current light travel distance because the galaxy continues receding during the journey, but eventually the spacecraft arrives. Now, suppose the target galaxy is beyond the event horizon, receding faster than light. The spacecraft travels at light speed, but the galaxy recedes faster. The spacecraft never catches up. It travels forever through expanding space, never getting any closer to its target. In fact, it gets farther away in terms of the expanding coordinate system. The spacecraft is like a person running on a treadmill that accelerates faster than they can run. They exhaust themselves, they run as fast as possible, but they make no forward progress. This is what happens to any attempt to reach beyond the event horizon, even at light speed. The destination recedes faster than you approach it. Some people suggest that we could send generation ships, spacecraft designed to travel for thousands or millions of years, carrying multiple generations of humans who would live and die aboard the ship during the centuries-long journey. Generation ships are a staple of science fiction for reaching distant stars within our galaxy. But could they reach galaxies beyond the event horizon? No. The problem is that expansion continues during the journey. Suppose you launch a generation ship at a significant fraction of light speed, say 90% of light speed, aimed at a galaxy that is currently 10 billion light years away. The journey would take more than 11 billion years from Earth's perspective, accounting for time dilation and the ongoing recession of the target. But during those 11 billion years, space continues expanding and expansion continues accelerating. By the time your generation ship approaches the location where the galaxy was when you launched, the galaxy has been carried farther away by expansion. The ship never arrives because the destination is always receding faster than the ship can approach. You have not closed the distance. You have merely exhausted resources and time on an impossible chase. Generation ships work for targets within the gravitationally bound local group where expansion is negligible. They do not work for targets beyond the event horizon where expansion dominates. The more you examine potential escape methods, the clearer it becomes that none of them work. Every attempt to breach the cosmic horizon fails, not due to lack of energy or materials or engineering expertise, but due to the fundamental physics of space-time and expansion. This is not a technological problem, it is a physical impossibility. The difference is crucial. A technological problem is something we might solve with better tools, better understanding, better resources. The Wright brothers faced a technological problem when trying to achieve powered flight. Engineers faced a technological problem when trying to reach the moon. These problems were difficult, but they were solvable in principle. The cosmic horizon is not a technological problem, it is a fundamental limit imposed by the structure of reality. It is like asking whether we can build a machine that creates energy from nothing, violating conservation of energy, or asking whether we can construct a square circle. These are not engineering challenges. They are impossibilities, contradictions with the basic rules that govern existence. Breaking through the cosmic horizon requires violating either the speed of light limit or overcoming expansion that occurs faster than light. Both are impossible. The speed of light limit is a consequence of space-time geometry and causality. Expansion faster than light is a consequence of dark energy and the dynamics of general relativity. Neither can be overcome by technology, no matter how advanced. Some people argue that we cannot know what future technology might achieve, that advanced civilizations, millions or billions of years ahead of us, might have discovered physics we cannot imagine, might have found loopholes or workarounds that we do not yet know. This argument sounds reasonable, but it misunderstands the nature of fundamental limits. Fundamental limits are not like technological barriers that cleverness can overcome. They are boundaries of what is logically possible within the structure of physics. A civilization a billion years more advanced than us will still face the same speed of light limit. They will still live in a spacetime where faster than light travel violates causality. They will still inhabit a universe where space expands due to dark energy. These are not details of our current level of understanding. These are fundamental features of the reality we all share. An advanced civilization might have better telescopes, better spacecraft, better energy sources, but they will still be trapped within their own cosmic horizon, just as we are trapped within ours. They might have learned to accept this limitation with more grace than we do. They might have developed philosophies that make peace with cosmic isolation, but they cannot change the unchangeable. The cosmic horizon represents an absolute barrier, not a difficult barrier, not a distant barrier, not an expensive barrier, but an absolute barrier. Absolute in the sense that no amount of effort, intelligence, technology, or time can overcome it. The barrier is written into the laws of physics. It is enforced by the structure of spacetime. It is permanent for as long as the universe continues expanding and dark energy continues driving acceleration. This is the reality we must accept. We are trapped in a finite bubble of spacetime, forever separated from the vast majority of the cosmos. No science fiction technology will save us. No future discovery will open a path. The walls of our prison are not made of matter that can be broken or energy that can be overcome. They are made of geometry, causality, and the expansion of space itself, and those walls are unbreakable. We have explored what we are losing, what the walls are made of, and why we cannot breach them. Now we must confront what it means to live in this cosmic prison, what implications our confinement has for our place in the universe, and how we should understand our existence in light of these inescapable boundaries.